in real life, we deal with both periodic signals and we deal with aperiodic signals. It would be nice to have a unified theory. It would be nice to be able to talk about the transform of a periodic signal kind of in the same language as the transform of an aperiodic signal. And for that, we use the following observation, which is a little bit of it requires a little bit of sort of kind of like the same sort of thing we had to do when we talked about the Fourier series of a periodic impulse train. So what we're going to do is we're going to look at as an example at x of t equals e to the j omega naught t. Okay, so this is a periodic complex exponential with fundamental frequency omega naught. Now what we know is that the Fourier series of this guy, so remember this thing has, we want to represent it as a linear combination of harmonically related complex exponentials. So, in other words, I want to represent it as the sum of a sub k e to the jk omega naught t. What's the Fourier series of this guy? What are the terms that we need to use in here to get this? Which harmonic do we have to include? What should k be to give me e to the j omega naught t? 1, somebody said. K equals 1. Right? If I put k equals 1, I get e to the j omega naught t. That's what I'm after. So if I set a sub k equal to 1, and then set all the others, a sub 1 equal to 1, and a sub k equal to 0 for k not equal to 1, that's it. That's my Fourier series representation. It almost seems too easy, right? It's e to the j omega naught t is equal to e to the j omega naught t. There it is. Okay, so now the question is, how should we think about this as a Fourier transform? We want to think of a continuous time signal. This is telling me that I have basically my Fourier series, if I plotted it out, would look like this. It would be 0 everywhere, except at k equal 1, where it's 1. So if I wanted to think of like a continuous function of frequency, now imagine that I again convert these to frequencies. So I have an omega scale which corresponds to my index of my Fourier series. I want now a continuous function of omega that makes me think of this. Well, what comes to mind? An impulse, right? That would be kind of a continuous time signal that's concentrated at this. It would have to be an impulse at omega naught. So your first guess might be that for e to the j omega naught t, if we want a continuous function of frequency that basically tells us, hey, this guy is concentrated at omega naught, your first guess might be to say, well, for the Fourier transform, I want e to the j omega naught t to go, now I'm going to be under the Fourier transform, not the Fourier series. Your first guess might be to make it an impulse sitting at frequency omega naught. That would be a very reasonable guess. But we know if it's going to be a Fourier transform, it's got to satisfy these equations. We're after sort of a consistent theory that will be consistent for both aperiodic and periodic signals? Well, if I evaluate now the integral, so I'm going to guess that x of j omega for that periodic complex exponential, I'm going to guess that it's delta of omega minus omega naught, which is precisely the thing that looks like what we're after. Here's omega naught, and it's got the value 1 there and 0 everywhere else. That's our kind of continuous frequency version. But we run into a problem. If we plug this into this formula, which came out of our derivation for the finite duration signals, when we plug in delta of omega minus omega naught, what we know is that that becomes a delta function at that frequency times the evaluation of this at omega naught, which is e to the j omega naught t. So if we evaluate that, what we end up with, well, using that sampling property of the delta function and the fact that the delta function integrates to 1, we actually end up with e to the j omega naught t divided by 2 pi. It's not quite what we want. We want it to be exactly e to the j omega naught t. So what do? We say, well, this didn't work, so let's make it work. Let's put 2 pi in front. And now, when I plug this into the synthesis equation, I get that out. Well, now you can play that game at every frequency. You can play that game at every frequency. So what we really want is we want it to look like this. That's my x of j omega. Kind of a kludge, but it makes it work. Kind of motivated by the reality of where the signal's concentrated, namely at frequency omega naught. But we have to throw in that factor of 2 pi to make the thing converge, to make it give us the correct synthesis equation. And so now what we do is we just generalize that to an arbitrary periodic signal. We take our x of t is equal to the sum of ak e to the jk omega naught t. So now I have my Fourier transform over here. My Fourier transform has become 2 pi times an impulse, which is concentrated right at that frequency omega naught. And now I just say, well, the same thing's going to hold for all of these exponentials. Each one of those is going to go to an impulse concentrated at the appropriate harmonic. So the term that has ak as the coefficient, e to the jk omega naught t, it's going to give me a harmonic at frequency k omega naught, the kth harmonic, with coefficient k. But to make the synthesis equation work, I have to put that 2 pi in front. Okay? So that's how we extend now the whole theory of the transform, which is based on the Fourier series. We now extend it so that we have a single notion of a transform, a function of continuous frequency for basically any single signal we can imagine, whether it's periodic or not periodic. And that'll be very useful when we do things like signal modulation, where we take a waveform which may be our message, a finite duration, terminator telling you that his brain is a neural network, and we multiply that by a cosine signal because we want to modulate it so we can transmit it through the air. And so there we're dealing with continuous time periodic signals and continuous time aperiodic signals. We'd like to know what's going on in the frequency domain there. And this allows us to do that. Now, the other thing I wanted to just review quickly is the basic properties of the transform. They're going to look very similar to the properties of the Fourier series. So I'm not going to dwell too much on those except for a few that turn out to be critical for our applications. So there's linearity. You take the sum of two signals, or a linear combination, and the transform is going to be the same linear combination of their transforms. Time shifting, x of t minus t naught, well, it's going to have the same transform as x, namely x of j omega, but with a phase factor in front, e to the minus j omega t naught. So notice that this factor in front, what time shifting does is it applies a frequency-dependent phase shift. You can see that the phase is minus omega t naught. So it's a frequency-dependent phase shift, but it's linear in frequency. The scale factor is just t naught. Conjugation, if you take the signal x of t and conjugate it, its transform is just x, the transform conjugated, but reversed, but flipped. So x conjugate of minus j omega. And that means that if x is real, then it satisfies this so-called conjugate symmetry property, just like the Fourier series. X of j omega, if the signal is real, will be x conjugate of minus j omega. Time reversal, just you reverse the signal, then you flip the signal, then you flip the transform. I'll just mention a few others, and then I want to talk about the ones that we're going to use in applications a lot. Well, this one will be useful too. This is the differentiation property. If you take the derivative of the signal, you multiply the transform by j omega. So think about what that means. For the high frequency components, they get linearly boosted. In other words, they get boosted by multiplying by j omega. So it's actually kind of, I shouldn't say linearly boosted. It's really, it's, when you think of what that does, is it's kind of boosting if it's, got high frequency content, then it's multiplied by, in magnitude, by omega. So yeah, I guess refer to that as linear. And then integration is sort of going to be the flip side of that. So you'd expect sort of 1 over j omega, and we get that. But then there's this thing right here, and this relates to the transform of the step signal, because remember, integration is convolving with the step signal. And what we're going to see in a moment is that when you convolve two signals, you multiply their transforms. So all we've done here is multiplied x of j omega by the transform of the step signal, u of j omega. And there's a time scaling property. What happens if you scale the signal by a? This should be x of at goes to this. And then there's Parseval's relation, which is just like the analog of Parseval's relation in the Fourier series. When you take the average of essentially the energy in the whole signal, the integral of x of t magnitude squared, you get the same thing if you take the integral of the magnitude of the transform squared, normalized by 2 pi. So you can, again, get an idea of the total energy content in the signal in both domains. So let me now turn to a property that we saw examples of called duality. And what it says basically is this. Suppose you have a signal x of t that has a transform or spectrum x of j omega. If you have a time domain signal, y of t, whose shape as a function of time looks like the shape of the transform of x, viewed as a function of frequency, then the transform of that y of t, namely y of j omega, is going to look like x of t. So this is the way of formally saying that. You have this function y kind of looks like the transform of x related by this equation. Then it tells you that x and y, those functions sort of relate to one another in a dual fashion in the two domains. And the best way to view that is with an example. Here's the isolated rectangular pulse. We saw that its transform is a sinc function. Well, if you now look at the this is in frequency. If you now look at the time domain signal, which is a sinc function, its transform is exactly an isolated rectangular pulse in the frequency domain. So we'll make use of this a lot, especially when we start doing things like reconstructing signals with low-pass filters. So this basically looks like a low-pass filter, ideal low-pass filter. And of course, this is sort of a perfect rectangular pulse in the time domain. Another example that kind of drives home this idea of duality is if you look at an impulse in the time domain, we saw that its transform is a constant in the frequency domain. And we saw that if you take a constant signal in the time domain, its transform is an impulse in the frequency domain. So this idea of duality kind of is a way of formally describing these kinds of pictures where you get sort of the same picture in both domains, but kind of flipped. Okay. Now I'm going to now talk about two of the most important properties. The first one is the convolution property. So the convolution property tells us what happens when you convolve two signals and then take the transform of that. Now, why should that be important? Well, where do we see convolution happening a lot? We see convolution happening a lot when we take a signal x of t and we put it into an LTI system with an impulse response h of t, and what comes out is the convolution of x of t with h of t. So a very natural question to ask is, if I have a signal with a spectrum, a Fourier transform, x of j omega, and I have my LTI system with frequency response h of j omega, what can I say about the frequency response of the output? So, does anybody know what that is? We can kind of think of it as being, heuristically, it's as if we're taking this signal that has this transform, putting it into this box that has this as the frequency response, and out comes this. Anyone want to guess? It's the product, right? Now that's very attractive, right? Because we know from experience that doing convolutions can be sort of a pain. Doing multiplication is about the easiest thing you can imagine doing. So what this means is that by going into the frequency domain, so this is kind of the frequency domain picture. What it means is that by going into the frequency domain, we can get a very nice understanding of what's happening when we put a signal through an LTI system. And this is an example of the convolution property. One example. The general statement of the convolution property is just given here. So you could just take any two signals. We can take the convolution in either order. So h of t convolved with x of t is the same as x of t convolved with h of t. And what the result is just as I indicated there, is that it's in the transform domain, it becomes the product. And the proof is just a direct calculation. I'll just go through it quickly. Here's the description of the convolution. This is actually what we typically would write as x of t convolved with h of t. And then what we do is we just transform both sides because these are equal signals. So y of j omega is the transform of this. Well, we just apply the definition of the transform. This is nothing other than the analysis equation. We multiply it by e to the minus j omega t. So that's the signal that's our y of t. We're multiplying it by e to the minus j omega t, and we integrate. And now what we do is we just say, well, wait a minute. Here we were integrating with respect to tau. Why don't I just switch the order of integration? Let me integrate with respect to t first. So then that x of tau can come outside the t integral. And I have h of t minus tau e to the minus j omega t dt. Well, that looks a lot like a Fourier transform. In fact, it's the Fourier transform of the time-shifted version of h, of t. It's shifted by tau. So now we can apply the time-shifting property. And what we get is h of j omega plus this phase shift, this linear phase shift factor. And now we're left with this integral. We're integrating with respect to tau. Well, these guys don't have anything to do with this h of j omega, has nothing to do with tau. And this is e to the minus j omega tau. Well, this looks exactly like, if we pull that h of j omega out, this is nothing other than the Fourier transform of x. So we end up with x of j omega times that h of j omega, and we get the product. Okay, so it's just a straightforward application of the analysis equation, but making use of the time-shifting property of the Fourier transform. Now, there's another property which is going to be very important, which is the multiplication property. So this was the convolution property. So it's going to show up basically whenever we're dealing with an LTI system. Then there's the multiplication property, which you can think of as the dual. We've sort of said that when you have something in the time domain, you have sort of A in the time domain corresponding to B in the frequency domain, then in some sense B in the time domain corresponds to A in the frequency domain. Well, that applies to properties too. So the multiplication property is sort of, again, kind of flipping things around. Here we saw that convolution in the time domain became multiplication in the frequency domain. So the multiplication property is the dual of that, which says that if we have multiplication in the time domain, it should become something like convolution in the frequency domain. But it turns out there's a little bit of a scale factor to make it all work out. It becomes 1 over 2 pi times the convolution. Okay, so this is dual to the convolution property, which we saw was this. So again, if we want, we can kind of draw our sort of duality arrows and see how the roles of multiplication and convolution get flipped.